Good morning. How was your first day? Very good. We seem to have lost a few people, but it's okay. So I sent Arpan some files, and he has circulated them to you. Uh, as part of that package, you have some files which are called wastewater from waste to resource. And these are just some case studies that I came across, which they don't give a lot of details, but it's good to know. For example, in a country like Bolivia, they what did they do? They covered the anaerobic ponds, and then they got energy. So they generated energy from a wastewater treatment. Similarly, and I'm not going to bring up on the screen, you have all of them. If you look at the case of Pradesh, Brazil, they did something in terms of financing to increase wastewater coverage. But there are all these files: Cairo, Egypt, Antonilco de Tula, Mexico, Durban, South Africa. So the idea being, if you read them, and these are very short files, one pages, two page, one page, two pages, like that. So when you read them, you'll get a much better sense that in terms of sustainable practices, what sustainable practices, of course, in the wastewater treatment context, what some other countries have done. Okay. Uh, Again, they will not have a lot of detailed information, but it's good to know. For example, in terms of financing, what is new, and we will not get chance to cover that. See, until now, when we talk of financing of a project, how do we do it? Well, we say we will put a wastewater treatment plant in this city, and it would cost so much, so many crores, let's say. So then we look at what are the places from where we can get financing. Of course, if it is a government project, then the government will finance it. If it is a private company, the private company will raise money from, let's say, the financial markets, and then they will do it. If it's a public-private partnership, then depending on how it is sketched out, these agencies will have to raise the finance. But typically, what happens is you raise the money, lead the project, and then you get some return on this investment by charging the consumer, for example, or whatever. But in one of these files, you will see that they came up with a very innovative financing mechanism where they said that this financing would be based on the results, not really based on the scope of work. So, how much of objectives you can reach, what percentage, based on that, you will be given the financing. So it's a very new concept. So these kinds of things, it's good to know, right? So any questions based on what we covered yesterday? Questions? Very good. So then we chug along. Today we will look at phosphorus, but before that, I want to give you a little bit of an idea. It's in a way continuation of what we did yesterday, but it will also have some new material. So we will look at phosphorus, but the overall scheme of things would be in agricultural waste management. But then I will transition to wastewater treatment, and at the end you will see that the principles are pretty much the same. Whether you are doing what we call tertiary treatment. Tertiary treatment means when we talk of wastewater treatment, When we talk of primary wastewater treatment, we are talking of removal of solids basically. And these are, of course, suspended solids. And in our case, we are looking at volatile suspended solids because they are the ones which contribute to the BOD. If you look at secondary, then we are looking at dissolved solids. And again, in this case, we are looking at volatile dissolved solids, also known as organic dissolved solids. Okay. So, if you look at kind of an old wastewater treatment plant, what would it do? It would bring in the influent, it would go through a screening, followed by a grit chamber, followed by a primary clarifier. In the primary clarifier, you will settle out the solids. But still, you will not be able to remove most of the BOD because, as you know, most of the BOD or the oxygen demand is tied up with dissolved solids. So then you bring them to the secondary treatment, activated sludge being the most common. So after primary treatment, you bring this to an aeration tank or an activated sludge unit, and then you convert the soluble organics into biomass, bacteria, and then you settle out the bacteria, and then this solids line from the primary and the solids line from the secondary, you typically take to an anaerobic digester. But this, even though it takes good care of the organics, it does nothing for the nutrients. So now we bring in this third layer called tertiary. And in tertiary treatment, we are looking at nitrogen and phosphorus removal. This is where I will spend most of my time. Okay. So what I'm trying to say is that although our focus will be tertiary treatment to remove phosphorus, today phosphorus, tomorrow nitrogen, we are looking at it from the perspective of agricultural waste management because the demand, the need for agricultural waste management is very high, and I'll give you some data on that. Okay. But we will eventually transition into tertiary treatment. So we saw yesterday that the drivers are basically population. Now, when you look at population, there are all these models. But one, oh, I think this one has run out of battery. Can you give me the pointer that we used yesterday? So, when you look at population models, then it's when you try to predict population in the future, it's an uncertain science. So there are models which, for example, we know the past history of the population. From there, we project. If you go to a very high rate of population growth, you see that we are looking at a population. We are looking at a population of, let's say, 16 billion. Population of 16 billion, but I think this is not going to happen. The better chances are there. But whatever they are, we are looking at a much higher population which has to be fed. Okay. So then, as I said yesterday, I would like to spend a little more time on this today. As we look at population growth and as we look at advancement of regions or countries, advancement meaning economic advancement, then we see, maybe with the exception of India, we see that the advancement of a society correlates very well with meat consumption. So if you look at industrialized countries, meat consumption, kilogram per year, you see in 2030, this is what they are projecting. 100 kilograms of meat protein per person per year. Okay. Whereas if you look at, let's say, sub-Saharan Africa, it will be much, much less. But the point being that these bars, typically you see, are much higher bars. So not only is the population growing, but the per person meat consumption is also growing across all regions, including India. But India is an exception because, as I said yesterday, and as you know so very well, uh, we don't know the true figures, but a good percentage of India is vegetarian. So this thing, meat consumption, doesn't really come into that picture. But anyway, the point being that these two together, the population increase and the increase in meat consumption, they produce a lot of environmental challenges. Now, when you look at meat production, then it so happens, for a variety of reasons, we will not get into the details, that the chicken growth rate is the fastest compared to all the others. And the reasons, agricultural scientists have lots of reasons. We will not get into that. But with chickens, the thing that happens is that, at least in the US, I mean, here you still have many, many places where chicken is kind of grown locally and slaughtered locally. But in most advanced societies, what has happened is that chickens are grown in very, very confined places, and it's highly centralized. So if you look at the United States map, the total is about 30 birds per person. But these areas, what we call the South and the Midwest, these areas are the places where all the chicken is grown. And as you can see, these dots, one dot is 2 million broilers. So you see that there are these very hot spots, which are the places where most of the chicken is grown. Okay? Now, the problem here is that if you have so many broilers in such a small land, such a small area, then that land gets challenged and the waterways get challenged. So, you have this runoff from excessive livestock feeding, and that runoff, we are looking at phosphorus now. The phosphorus in that runoff creates all kinds of environmental problems because it releases phosphorus, let's say the dissolved phosphorus immediately, and then phosphorus gets into the sediments, it ties up in the sediments, and it comes into some kind of a quasi-equilibrium, and it slowly releases the phosphorus. And this goes on for decades. So if you look at the US, we are looking at phosphorus. If we do a phosphorus budget, then fertilizer runoff and livestock together, 34 plus 16, it's about 50% of the phosphorus that is discharged in water bodies comes from these two sources. And these nitrogen and phosphorus together create so much of environmental challenges that one of the ways in which we deal with that is through this called TMDL, total maximum daily load. So states and regions have fixed the amount of nitrogen and phosphorus that you can discharge. Okay? And though these numbers sound very big, 186 million pounds, but you have to keep in mind this is much, much lower than what we are discharging today or what we were discharging 10 years ago. So many of these states, so look at this map, this is the Atlantic Ocean. This is the state of New Jersey. This is New York. This is Maryland. This is Virginia. So this peninsula is called the Delmarva Peninsula. Delaware, Maryland, and Virginia, all these. And this bay is called the Chesapeake. a very scenic place. Uh, for example, one of the best aquariums in the United States is on this bay, the Baltimore Aquarium. For fishing, it's a very good place. For tourism, it's a wonderful place. But because of this very high discharge of nitrogen and phosphorus into this bay, we have lots of these algal eutrophication problems. So what they decided to do is they decided to limit the supply. And what that means is that now if you grow chickens, then you have to think very seriously about how to handle the waste that is generated by this chicken industry. And then if we look at phosphorus, the most important thing about phosphorus is that it's a non-renewable resource. We have only a finite amount of phosphorus available. And that we mine phosphorus just as we mine coal. We go to the sources, and these sources, they are not spread uniformly throughout the world. Phosphorus deposits are concentrated in North Africa, United States, Eastern Europe, China, South Africa, and Finland. So you see that the whole world needs phosphorus, but the places which supply are very, very limited. So, I mean, you do have a lot of phosphorus that is in reserve, let's say 67 million tons. We mine about 1/5 of a million ton every year. But that is kind of a little deceptive because what happens with any resource, any ore, for example, is there are two kinds. One is what is called readily exploitable. That means you have good quality of that. And the other one is it's available, but you have to spend a lot of energy and a lot of money in getting the resource out of it. So some models predict that the readily exploitable reserves of phosphorus will start to deplete in the next 45, as early as 45 years. 45 years is not a very long time. If we are looking at phosphorus which has been used and mined for hundreds of years, and in that context, 45 years if it is depleted, that will be a major environment, major kind of industrial problem. So people have looked into this and they say that based on, again, what is the usage, different scenarios, they predict something like by, let's say, 2070 or 2100, we will be out of the readily exploitable reserves. So that's a big warning sign, big danger sign. So when we are looking at poultry, as we saw in this picture, what do? You build these facilities where you crowd a lot of chickens in a very, very small area. So what do you do with that waste? That is the issue. And we know that this waste, it contains high amounts of phosphorus, ammonium, potassium, magnesium, calcium, because it's in the feed. What we feed the chickens does contain these elements. So it is nothing surprising that we do find them in the waste as well. And the idea then is that if we can extract the phosphorus from this poultry litter, and if we can separate it, then we may be able to recover phosphorus. That's the governing principle. But we know that with phosphorus, there are other things as well. So, for example, what I'm showing is one particular source, commercial chicken farm. You go to the litter, and when you take the litter and then you analyze it, and you see that you get potassium, magnesium, calcium, ammonium, sodium, sulfate, phosphorus, and also nitrogen. And then the question is, well, how much can you extract Well, that depends a lot on what is the pH and what is the matrix. So, as I was answering to a question yesterday, what one has to do is one has to do some aqueous chemistry modeling. And there are these very good softwares available, Minicule being the one that we use. And there you look at, well, these elements, what are their most common forms? What is their solubility product? And then what is the pH? I mean, what pH are you running at? So you can run these models. And what this is trying to show you is, and I know you may not be able to read it when I distribute this. So these are the possible compounds. Okay? And based on the pH, we can sketch these curves, and then we can add them all up to say, well, what will be the total concentration? So these help us in the sense that we have now what is known as the upper envelope. This is the upper envelope that we are interested in, because we want to know how much we can get at the most. Okay, so we look at the source, we look at the constituents, and then we do the model. And then this is what I will spend most of my time today. We came up with this kind of a process. Okay, we call it PEARS. PEARS stands for Phosphorus Extraction and Recovery System. And the way this runs is you bring in the waste. This is the poultry litter. You add an acid. Then you bring it, I mean, you first put it in a holding tank. You bring it to reactor 1 where you are, excuse me, you add an acid. Acid, as you know, will reduce the pH. Once the pH is reduced, the idea is to get the phosphorus from organic phosphorus into inorganic phosphorus, which is orthophosphate, and then raise the pH. And if you raise the pH now, because phosphorus salts, most of them are pretty insoluble, like potassium phosphate, potassium magnesium phosphate, or magnesium aluminum phosphate, or hydroxyapatite calcium phosphate. So these solubility products we know, and based on that, we can precipitate out the phosphorus salt. And of course, as you know, precipitation dissolution, its equilibrium doesn't really allow for a very high degree of removal. So what happens is that even after you have precipitated out the phosphorus, there is still lot means in this case about 20-30 milligrams per liter of phosphorus in this solution. So then we take this solution, we bring it to an ion exchange system, which is very phosphorus selective. And in that ion exchange system, we pretty much remove all the phosphorus, as long as this cartridge is not exhausted. So we get phosphorus-free wastewater, and this goes on until this cartridge is exhausted. When it is exhausted, we put in a regenerant, we strip out the phosphorus, and we again then manipulate the chemistry so that we again get another round of phosphorus salt. So we are getting phosphorus salt here, phosphorus salt here, after we regenerate. And these two together, we have seen give us, you may say, about 95 to 96% of the phosphorus that was present in this waste we can recover. Okay, but when we talk about sustainable process, we can't just do it once through. So what we have to do is we have to reuse the solutions. So when we are using the acid solution, the question is, can we reuse the acid solution? That means we put in an acid, we extract the phosphorus out, we then take it to the next reactor, and then when the phosphorus salt is precipitated, can we reuse the acid and the base? That's number one question. If you look at this part, when the cartridge is exhausted, when you regenerate the cartridge, from that regenerant, you precipitate out the phosphorus salt. Can you recycle the regenerant? So these kinds of questions become very important if we have to develop a sustainable process. And then I'll show you some data. And of course, today we are focusing on phosphorus, but all the time we have to keep holistic in mind. But here there are these what we call WBS, washed biological solids, and those we can put them into an anaerobic digester, as we discussed yesterday, or our current focus is on biochar, and I'll not get into the reasons, but one can look into biochar as well. That's the idea. So keep this picture in mind, not the whole details, but basically these three steps: acid, base, ion exchange. Questions? Yes.
In exchanger phase,
Yes.
You extract the phosphorus from reactor.
Yes.
But when you regenerate it, this after regeneration, this solution contains both phosphorus as well as some salt.
Oh yes. So sodium chloride is the most common salt. Yeah.
So when you add these two solutions, then final phosphorus composition or concentration may be changed. So you can again use it in cyclic way.
So the final phosphorus salt is a solid phase, so it is precipitated out.
Okay. So
that is the only way perhaps in which you can recover the phosphorus.
So after regeneration, you again precipitate it.
Yes.
Okay.
We have to raise the pH again.
Okay.
I'll show you the data. Any other question? Okay, so now let's look at what are the phosphorus products that we are looking at. We are looking at hydroxyapatite, which is this formula, calcium phosphate hydroxide, and you go to standard sources, and you find out their solubility products. Though I have to say, first of all, getting solubility products very easy from these sources, but the sources do vary. That means if you look it up in Handbook of Chemistry and Physics, solubility product of hydroxyapatite may be different from the solubility product that's given in some papers where they also looked at this. So there is some variation. And then there is some variation even within our experiments. So when we run experiments, we have to sometimes change these numbers based on what we get. Okay? So these numbers, of course, they will not vary by a lot, but they do vary sometimes. Keep that in mind. So you look at hydroxyapatite, struvite. This is what I will focus most on because this is what we have been working most on. This ammonium, magnesium, phosphate. And struvite is a very good fertilizer because it's what we call a slow release fertilizer. What happens with the fertilizer is there are two kinds. One is put this fertilizer on the farm, and if it means water, then all the nutrients come out. I mean, a fertilizer basically goes by three elements, as you know. You know, in the United States, we write a fertilizer with a Z or a Z. Here, you would write it with an S. So, there are these three components: nitrogen, phosphorus, and potassium. So, there are two kinds. One is what we call burst release. First release means, as the word itself sounds, the moment it meets water, this solid fertilizer, the moment it meets water, all these nutrients come out. And this might be good in some cases, but most of the time, what this does is it releases all these nutrients. The plants can take up only so much, and the rest of it goes as runoff. And the other one is slow release. So we are more interested in slow release. And it so happens that struvite is a slow release fertilizer. So we prefer to get struvite. But as you can see, we can also get MKP, which is known as potassium struvite, which is potassium magnesium phosphate. So if you look at these three constituents, NPK, in order to get NPK, we have to have a mixture of these two, because this one has N, this one does not. This one has K, this one has not. Okay, so ideally, we are not there yet, but ideally, your process should be such that you can manipulate it in such a way that you get a combination of these two, which will give you the amount of NP and K that you need. It's very easy to say, very, very difficult to achieve, because the precipitation, the crystallization, those steps, they are very complex, and no matter how best you model them, the experimental results always defy our models. But I mean, I'm talking of kind of very detailed experimental results, but the fact remains that we can get either struvite or potassium struvite very easily. So even if we are not able to achieve this right balance, if we can get almost all the phosphorus as struvite, let's say, we are doing okay, because today at least our focus is on the phosphorus part. So today, it does not really matter whether we get it as hydroxyapatite or struvite or potassium. Okay. But if you talk to agricultural scientists, for example, they would like to get a mixture which has all these components. And of course, when you get these compounds, you have to do a very detailed characterization. So this is an SEM EDX of these three. So the hydroxyapatite, you can see these grains, and then one looks at, well, how you can do X-ray diffraction and all kinds of characterization, just because we want them to be as crystalline as possible. And struvite, what happens to be is it's very flaky. Why? There are some crystallinity issues that I will not have the time to get into today. If you are interested, I can cite some of our publications. If you read them, you'll get a little better idea. But all I'm trying to say is that, first of all, when you get these, you have to characterize them. And most importantly, you have to see what kind of impurities there are. Because if you want to sell it as a fertilizer, if you're claiming that you are making a fertilizer, then there are very strict regulations governing claiming something as a fertilizer. So that you have to make sure that the impurities are less than what is allowed.
Sir,
yes?
You determine the purity of fertilizer by characterization technique. Means you are using some X-ray diffraction technique, that's amount of phases present in your material.
No, actually these are two different things. When we say purity, we are just looking at when we say hydroxyapatite, then what we are getting is the calcium and the phosphorus and the oxygen and the hydrogen in the ratio in which this.
Okay.
And most often, or more often than not, what we see is besides calcium, there might be a little bit of magnesium. There might be Sodium. Sodium is the most common problem. So that is what I'm calling by purity. Then within this, whatever you have, if let's say I can remove the sodium and the chloride and all that, then we look at the crystallinity, because that then in turn defines whether it will be slow release or burst release. So the more amorphous it is, the faster it will release. That's the idea. Any other question? Very good. So then again, we come back to this slide which we have seen before. The idea is now you start comparing, because now you have seen what all are in your precipitate, and you can then go back to the model and see whether indeed we have been able to get most of this phosphorus out or not. And you can say, well, why really to go back to this model? We will just look at how much phosphorus we have recovered. We know how much phosphorus went in. So from the difference, we can know. And that is correct. But as I said, our final goal, keep in mind, is to come up with a process that is versatile enough that you can then start to shift these. So if I want more of calcium hydroxyapatite, what do I have? If I want more of struvite, what do I have? So that's the final goal. I'm not claiming we have reached there, but that's the reason why you have to go back to the model. Okay, so what's the general scheme? You bring in this poultry litter, and in our case, the farm is 200, 300 miles away from my campus. So when it comes in let's say 10 kilogram batch or 20 pound batch, when they mail it, it says Sukalyan Sengupta, Department of Civil Engineering, University of Massachusetts. So they bring it, our receiving office brings it to my office. And what I have seen is that before we started with this project, I used to get a lot of students come to me during my office hours. Once these packages started to arrive, the odor is so horrendous that students now, they run away. But anyway, we have to do what we have to do. So we take it to the lab, and then we make a slurry out of it. And then finally, based on what we are adding, we then recover. Okay. So this is just to give you a visual idea. And as we know from aqueous chemistry, pH is such an important variable. So when we add an acid, of course, the organic phosphorus is very easily converted into orthophosphate phosphorus. But we have to see what is the most optimum pH. And what we found is that if we can reach a pH of about 5, that is very good. We don't have to go much below that. But what is also very important is that the dissolved organic matter is a big factor in all this. That the more you have dissolved organic matter, then that creates kinds of disturbances in your model. Because all the models that we did, these models do not have any dissolved organic matter component. These are all based on just the solubility products. Now, if you bring in dissolved organic matter, that creates all these challenges. And where is the dissolved organic matter coming from? Because this is chicken waste. So as I was describing yesterday, what happens is, in order to keep these chickens so close together, they inject a lot of hormones, and I mean, for them to grow fast, they inject a lot of hormones to prevent any diseases. They inject a lot of antibiotics. So we do have all these issues, which I will not address today, except only to say that this dissolved organic matter does play a role in phosphorus extraction and recovery. But phosphorus, as you know, it's a triprotic acid, to write it down for you. This is very classical aqueous chemistry, that if it's a triprotic acid, it will give up one of its protons and then it will form diprotic, that again will give up one of its protons to form monoprotic, that again will give up the remaining proton to form phosphate. So when we say orthophosphate phosphorus, we have to keep in mind that it is a distribution of all of these species. Now, of course, as you see here, the first pKa of this system is 2, and the second pKa is 7. The third pKa is 12, with hardly affects us. So when we are at a pH of, let's say, 7.5, 8, as it comes in, if you just mix this liquor with water, you will get a pH of about 7.5. And then you add the acid, the pH is depressed. So we need to understand what is the speciation. Okay, so at a pH of 5, as you can see, pretty much everything is HPO4 2 minus. And based on that, one can do some quick calculations on what is the acid demand, what is, how much acid do you need to bring it down to this pH of 5, and then how much base do you need to precipitate out the phosphorus. But as you see, it also correlates with UV254. UV254 is a very good surrogate for dissolved organic matter. And as you see here, this UV254 correlates very well. Okay, so what that means is that we do have to at least look at these basic parameters, these surrogate parameters. So then, if I want hydroxyapatite, I need some calcium, because the amount of calcium that's present in the waste is not enough. So I have to add calcium externally. And the easiest, the cheapest source of calcium is lime. So you add lime, and you can then get these hydroxyapatite. As you read here, we were able to achieve greater than 90% recovery at a pH of about 10. And the sample, when you do an SEM-EDX, you can look at the Ca to P ratio. And you do get magnesium, potassium as well. Even though you are not precipitating, you don't want to precipitate the magnesium and potassium. But as I said, you don't really have much control. The only two controls you have are how much acid you can add and how much base you can add.
It is easily precipitated, no? Because its K-speed level is very low.
Yes, it precipitates easily. But the question is, how pure is it? The dissolved organic matter. This is humic acids, fulvic acids, pharmaceuticals, all of them put together.
How they are affecting the system, that is what you are trying to.
Exactly. Why are we interested in that? Because, as you know, we are now in a situation where if you can claim farm-raised chicken to be cage-free and these pharmaceuticals free, then you can get a premium. In other words, to go to a supermarket, if you buy the regular chicken, that will be one price. If you can claim, and that claim is actually verified by the US Department of Agriculture, that it is cage-free and pharmaceutical-free, then you can fetch a higher price. So there are some, and we are looking at about 6 or 7 farms. One of them is an organic farm. So the organic farm litter also has less dissolved organic matter. And the question is, how does this dissolved organic matter affect our phosphorus recovery? And farmer in turn is interested that if I am spending this extra money to have it as organic, can I get this return by charging? That those are kinds of peripheral questions for us. But only thing that I can say is exactly what you asked, is that we are looking at UB254 to see what effect organic matter has on our process of phosphorus extraction. And so we have to go to a peak of about 10. We can produce true white, which is ammonium, magnesium ammonium phosphate. And this also precipitates very easily. Now, when we get true white, what happens is true white also happens to be of two types, and I'll explain that. All of them. Okay, so when we look at type 1, as you can see, type 1 is very crystalline, whereas type 2, very flaky. So why does this happen? I don't know the answer. We have some hypotheses, but we have not been able to do the detailed experiments that are needed. But all I can say is we get a mixture of type 1 and type 2. Now, it so happens that this one is more of a burst release and this one is more of a slow release. Okay, so as I said, we have been looking at 1, 2, 3, 4, 5, 6, 7 farms, and the data, they seem to suggest that the recovery is mostly limited by phosphorus release, which is again very, very logical. And the precipitation is pretty high. Precipitation in this sense means, when I say 100%, it means of how much I've been able to take out by adding the acid. And you get pretty good numbers. As I said, this is not the complete step, because this is now to this, whatever is unrecovered, we again put it to the ion exchange system, which is where I would like to spend most of the time. But all I'm trying to say here is that the overall is pretty good in terms of the salt that we are precipitating. And again, they tie very well to our models. Models also tell us that if we are in this pH, and if this is the constituents, then chances of these precipitating out can verify. All right, so back to this. So we talked mainly about this phase. That means you add an acid, reduce the pH, you get the phosphorus out of the organic solids. Now, as orthophosphate phosphorus, raise the pH, you get the precipitate. But now, I would like to move to this part. Now, before I move to that, acid addition, as you know, mineral acid addition is not a very friendly base, not a very environmentally friendly. So the question is, can we look at alternatives? And of course, when we talk of an acid, the alternative that comes to mind is carbon dioxide, because we know that carbon dioxide is a waste gas, or it's a waste material. Can we use its acidic properties to do the job for us here? And we have done a number of cases. I'll just show you one where, when we replace this mineral acid with carbon dioxide, our final goal is actually to get carbon dioxide from a flue gas. Right now, we are doing with pure carbon dioxide in the lab, but what we see is that if we replace the mineral acid with carbon dioxide, we get phosphorus at about 68 milligrams per liter. The sulfate seems to be much higher, and that will play a very important role, not necessarily in this first part, but much more so in the second part, because now when we get into ion exchange, this competition becomes very critical. And the chloride is not very high. 100 is pretty common, even in some drinking water sources, not sources, drinking water supply systems, we get chloride kind of getting to that. 60, 70 is very common. I don't know, anybody has any idea of the chloride level in typical drinking water here? My guess would be about 100, at least, I mean, less than 100. That would be my guess. Because chloride, as you know, it's not a primary contaminant. It is a secondary contaminant, because what happens is with chloride, the taste that is the issue. It's not really a health issue. And the secondary limit for chloride is 250. Anyway, I mean, we are not at all talking of drinking water here. So if you look at the cations, then you do have a lot of nitrogen, as expected, very high potassium, and which is great in terms of potassium sulfide, and then also magnesium and calcium. So what I'm trying to say is that if you replace mineral acid with carbon dioxide, you don't really have any compromise of process efficiency in terms of getting this phosphorus out. Okay. So then we come to the second part, that we have been able to get out as much as possible, and now this is effluent from reactor 2 is our influent into this. Upendraji, how long should we go this session? 15 minutes more? Okay. So maybe a good time to pause, because we are entering into another area. Questions?
This concentration outside.
Yeah.
These are the concentrations coming out of the reactor.
These are the concentrations in this.
What causes a higher percent of?
What is the cause? Don't know. It's just maybe in the feed. I don't know. It's not just a one-time thing. We have seen this consistently. So, cause I don't know. Any other question? Okay, so then we enter the second phase, which is something which I am directly involved with. This first part, I am only peripherally involved. So in the second part is what we are calling the polishing step. So this is post-precipitation. Can we extract whatever phosphorus we have not been able to extract in stage 1? And the governing principle here is that if we have orthophosphate phosphorus, then we know that oxides of polyvalent metals exhibit Lewis base absorption properties through formation of inner sphere complexes. So phosphate forms very strong inner sphere complexes. We know that. And the orthophosphate molecules, they do have this lone pair of electrons, and they are pretty strong ligands. So it is all coordination chemistry from here on.
What is the difference between inner sphere complexes and outer sphere complexes?
Okay, that in a moment. Okay. So, and it so happens that if you are interested, for example, in removing arsenic from water, arsenate chemistry and phosphate chemistry is very, very close, because both are oxyanions. So, some of the principles that I will talk about can equally be applied to arsenic removal. So now, if you have this situation where you have a ligand that you're trying to remove, then people, many decades ago, they started coming up with this concept of PLEs, a polymer which is a ligand exchange. And so, when we talk of ion exchange started basically with kind of non-selective resins. Could remove all the cations. For example, if you are in the hydrogen cycle, it would remove sodium, it would remove calcium, it would remove magnesium, all the cations. And if you are in the anion mode, you replace everything with hydroxide, chloride, the nitrate, so you will get pure water. That is how it started, the industry started. But then we started now making polymers which are specialized for specific applications. So maybe 20, 30 years after, I mean, the history of ion exchange, it pretty much starts with the Second World War, because we meaning in the United States, they had to purify uranium for the Manhattan Project. That is how in the 1940s ion exchange became really a mature technology. So 1940s it started. By 1970s, 80s, we had come up with the first version of these PLEs. But they were granular metal oxides. I mean, initially, if you look at a granular metal oxide, like iron oxyhydroxide being the most common one, you can use it to as a polymeric ligand exchanger, as something that will tie up the ligand. But if you have worked with iron oxyhydroxide or zirconium hydroxide, you will see that they are not physically very robust. Take them in the palm of your hand, you rub your hand, you will see that it becomes powdery. So the idea being that you can't really use them in a process that is supposed to run for a long time. So that's what I mean by the word lack mechanical strength and the attrition resistant properties for prolonged operation. You cannot really have a once use because these are so expensive. You cannot just have it once. You have to use them repeatedly. And if you look at orthophosphate phosphorus is an anion because we are looking at primarily H2PO4 minus and HPO42 minus because 7 is the pKa. So if you are, let's say, pH 6, this is much more than this. If you are at pH 8, this is much more. So we are basically looking at either H2PO4 minus or HPO42 minus. And if I want to remove this anion, if I go to a regular commercial anion exchanger, then I won't be able to do a very good job because these anion exchangers, they do not have much selectivity for phosphorus. As you saw in an earlier slide, I'll go back to it, there we are. We do have, compared to phosphate, we do have much higher sulfate and we do have chloride. So if I just use a commercial anion exchanger, then my anion exchanger will be loaded or will be saturated by chloride and sulfate. Only a very small fraction will have phosphorus in it, and that will definitely not make it a sustainable, viable process. So one has to come up with an anion exchanger that has high selectivity for phosphorus, which commercial anion exchangers do. And one has to have a form or a morphology which has the property that the granular metal oxides have, in that they're very good at removing these oxyanions. So you need a hybrid. You need a hybrid with the properties of granular metal oxides, but much higher mechanical strength, and the property of an anion exchanger, but with much more selectivity. So that's where these PLEs came into being. They combine the sorption affinity of metal oxides with the durability and mechanical strength of the ion exchange. That's the heart of this research. that how can we get an ion exchanger which does have the absorption affinity of metal oxides, where and also has the strength. Okay. So that's, and so the idea is basically you start with a polymer, which is in this case its name is it's a Dow product, and it's primarily, I mean, well, in our jargon it is called Dow 3. And so you see it's a free form. So it's a polymer, and you have one, two, three nitrogens. And as you know, nitrogen has this lone pair of electrons that it can donate. And this is bispicloylamine group. This is how you get it from the Dow company. I mean, we don't buy it from the Dow company; we get it from another supplier, but it's made by Dow anyway. So the idea is, and I'll stop with this idea, I mean, with this session. If you look at this, you can see that yes, this has some ligand exchange uh, kind of properties, but is there any way in which you can put in an iron oxide or a zirconium oxide, iron oxyhydroxide or zirconium oxide in this? Because if you can, then you will get the advantage. You will get the advantage of the iron oxyhydroxide removing the phosphorus, and this very robust, this is physically very, very strong. This is a commercial resin which is used for other applications, but this is used for hundreds of cycles. So you load it up, once it is exhausted, you regenerate it, rinse it, put it back again, and you go on like this for hundreds of cycles. So very, very robust. So that is the idea that we started with. And now, why did we choose this resin? I'll not get too much into the rotation chemistry or surface chemistry. But if you look at the alternatives, you will see that none of the alternatives has three nitrogen. These three nitrogens play a very critical role in becoming as selective to phosphorus as they are. So the nitrogens provide the selectivity, the iron oxyhydroxide provides the phosphorus removal part. So these two combined give, and we'll go through data. But that's the idea that we started to explore. I think I'll stop here. And Dr. Kumar, when shall we resume our next session?
After 15.
After 15 minutes. Very good. Questions?
Structure. Ligand is attached to the benzene ring.
No, the ligand is phosphorus.
Ligand is phosphorus.
Yes, the phosphate or the phosphate phosphorus. That is the ligand that we have to remove from the water. The ligand is not in here.
No, I'm saying that the water there is phosphorus.
Yes.
So you have to remove the phosphorus.
Yes.
So there will be some coordination bond with ligand with this exchanger. So this coordination bond will take place between this nitrogen.
Well, I mean, we haven't reached there. It all depends. If you look at this compound, then this compound is nothing but now I have preloaded to occupy these two nitrogen, the lone pair of electrons donated by nitrogen to copper. And now, when I put this in an ion exchanger column, when I pass my phosphorus solution, the phosphorus bonded to copper and also to the iron. So we will get to that. We'll get to that. Very good. So we will resume in 15 minutes. Thank you.
So we will go to the coffee shop and then we'll have coffee over there.
Oh, okay. Welcome back. So we were looking at phosphorus removal, and as I said, the idea is, can we come up with a resin with a polymer which has the selectivity that we associate with metal oxyhydroxides, and also the robustness, the physical toughness, robustness of a regular polymer. So the idea that we are exploring here is that we start with a free-form resin, which is a polylamine resin. This is how it comes in. And as you see, its particle size is about 300 to 800 micron. As you know, when you buy a resin, you don't get all the particles of one size. I mean, there's a distance. And it is a macroporous polystyrene with the divinyl benzene cross-linker. And now, if you start with a regular polystyrene divinyl benzene resin, you can get what is known as a quaternary ammonium anion exchanger, very common anion exchanger that you get in the market. It has many, many applications. What some people have done is they took this resin, and in this resin they impregnated iron oxyhydroxide, okay, nanoparticles. How they do that, it's a little involved chemistry. We will not have the time to get into it. But as you can see, there is a problem here. This nitrogen has a positive charge, right? And so this resin, when you buy from the market, it comes with some anion associated with this positive charge, which is typically a chloride. Now, in this, if you want to put in iron oxyhydroxide, it's not very easy. So one has to do some manipulation of process chemistry. You have to reduce and then oxidize. I will not get into this, but this is in fact, nowadays it's a commercial resin. It's called Arsenex. Arsenex. Or I think there is this E is not there, Arsenex. And what is this? This is this resin plus iron oxyhydroxide nanoparticles. We took a little different approach because we wanted to look at various kind of options. In this one, as you can see, the only way in which the phosphorus is being removed is through the iron oxyhydroxide. The resin really doesn't do anything. The resin just provides a platform on where you can impregnate it with this. Okay. In our case, we wanted to look at various cases. So if I look at this first column or the second column, I take this preform. I do nothing to the nitrogen. I just impregnate it with iron oxyhydroxide, pretty much like this. And the other option that we tried is I take this and now I tie two of these nitrogens. This is a Dow 3 and 3 nitrogens. I tie two of the nitrogens with copper. Very good, thank you. So what we can do, what we did do is we we took this resin and now we passed a copper solution. What will that do? Well, copper, as you know, is a very strong Lewis acid. Nitrogen is a very strong Lewis base, so they have a very good coordination bond. And why is this good? This is good because not only do you have this copper and the ligand, phosphorate, orthophosphate phosphorus, but this structure of the resin also gives you a very good place where this phosphorus, once it comes in, it cannot leave. So just removing the phosphorus is not enough. You have to make sure that it doesn't bleed out or leach out. But we were actually interested in something even better, at least in idea. And that is, I take this resin, I buy it, I then preload it with copper. And now I take this and to this I then impregnate it with HFO, hydrated ferric oxide. And this should be win-win situation because now the phosphorus, it can tie up with copper, it can tie up with the HFO. That's why this is a progression. We cannot just look at this in isolation. One has to see what part of phosphorus is taken up by the HFO, what part by copper, and do we really get 2 plus 2 when we put them together? That's the idea.
So this is specific selective resin, no?
This
resin?
Yes, it's selective for phosphorus. Yes, absolutely. Because of this copper phosphate bond. Because if you now look at the competitors to phosphate, the chloride, the nitrate, the sulfate, none of them can, I mean, they are pretty poor ligands. And that's where this inner sphere and outer sphere will come in. I'll come to that in just a minute.
The copper is attached with nitrogen by electrostatic.
Yes, not electrostatic. I mean, copper and nitrogen, because nitrogen has this lone pair of electrons, it donates it. So that's this coordination bond. Now this, when you pass this copper solution, you will pass it as we do with copper chloride. So there is a chloride here, and that chloride is being exchanged with phosphate. So the electrostatic part is with this one. But now you see when you have copper and chloride are pretty much bound just by electrostatic attraction. When you bring in phosphate, why does the phosphate knock out the chloride? That is because the phosphate not only forms electrostatic bond with the copper, but also the coordination. That extra coordination bond gives all this selectivity.
So ultimately, at the end, exchange will take place between chloride and phosphate.
Yes. I mean, we preload it with chloride. So in our case, yes, it's chloride and phosphate. But as you can appreciate, it will not be always just copper and phosphate. There will be a little bit of copper and sulfate. There will be a little bit of copper and nitrate. So the question is, we want to minimize all that, maximize phosphate. Any other question?
We are using, at the end, we are using chloride form, this system. At the end, we are using chloride
At the
form.
end meaning?
Means after inserting this oxide, nanoparticle inside this resin, we are using chloride form and exchange takes place between the phosphate and chloride.
That is for this copper. For the oxyhydroxide, there is no exchange really because that one, you know how it forms the oxygen, the bond with oxygen.
So I'm saying that instead of chloride form, if we use some kind of OH form resin, then
OH form resin, you have a problem because if it is a strong base resin, then you will have this spike in pH, which you don't want in the system. Once the OH leaches out, it will jack up the pH.
So then it will not work. pH ratio.
Any other question? Good. I mean, I would like you to ask me more questions so that I do less of the talking and I do more of answering questions. Okay, so what I did want to also show you is, well, in theory, you can put in hydrated ferric oxide, but you see, I mean, it's not as simple because there is a lot of steric hindrance. And how do you put in hydrated ferric oxide? Well, you will put in some ferric salt, and in this case we put ferric chloride, low pH, and then we raise the pH so that we form these nanoprecipitates of hydrated ferric oxide, which kind of stick in here. That's the idea.
But sir, I think there is some donut exclusion principle also there. Na? Suppose we sending some metal oxide, so inside you have positive charge, so it will replace your nanoparticles.
In this case, they solubilize the ferric ions and then you precipitate it
Inside
within the resin by raising the pH.
Exactly. So that was in fact going to be my next statement, that you pass this ferric salt and you have ferric ions pretty much kind of in a very concentrated form, and then if you raise the pH, then they will start to form ferric hydroxide, and that ferric hydroxide will try to find wherever it can hide or wherever it will. And so the trick is, I mean, I'm making things very simple. It's not as simple because the trick is to form the right kind, the right size of hydrated ferric oxide. Because we have seen, and others have seen this as well, it's no secret that your HFO nanoparticles should be, let's say, somewhere between 15 to 30 nanometers. That's the what we call the Goldilocks. That's the most perfect size. Now, how do you manipulate that? It's close to impossible. You try out different techniques. I mean, there are basically two techniques to raise the pH. One is you raise it up suddenly, and the other one is you raise it gradually. And without going into much of the synthesis chemistry details, the gradual jacking of the pH gives you better nanoparticles. Better means more uniform, closer to this 15 to 30 nanometers. But again, if you read the literature, we have been able to, for example, in this case, get, let's say, 45 to 60 milligrams of iron per gram of resin. And when we first submitted our first paper in this, the reviewers, one of the reviewers, comment was that this is very low iron load, and they cited a paper which had much higher iron load. So then we read that paper. That paper was completely different starting material. So what I'm trying to say is you can't really just compare like this, in the sense that you can't say that, well, some other group, they were able to load 100 grams, 100 milligrams of iron. So wouldn't that be a better resin? Not necessarily. In order for it to be a better resin, which means it takes selectively more phosphorus, it's not just how much iron loading. Of course, iron loading does play a role, but also the size and the uniformity. So keep that in mind.
Sir, ultimately you just determine at the end selectivity. If the
Selectivity and its equilibrium of the capacity, both. So it has to be selective, and it also has to kind of remove a lot.
Sir, if we minimize the size of the iron oxides,
How?
obviously,
How will you minimize? That is a very not easy question to answer.
its absorption capacity will be increased, surface area will be more.
Well, it's not just a function of only the surface area. Yes. I mean, what you're saying, I fully agree with it. But how? That's the question. Because if you talk to material scientists, they will give you ideas which are not necessarily implementable here in this context. So you have to keep in mind that this ion exchanger is a very strong electrolyte solution.
Yes.
So whatever is happening within this very strong electrolyte solution is very different from whatever is happening, let's say, in a synthesized, more or less pure solution. So I can only say, if you are able, whatever way I believe it, if you are able to manipulate the size of iron oxyhydroxide, then you can come up with a product that will sell like cotton.
How do you figure out what will be the pH within the solid phase? Because
Well, the pH within the solid phase, when you are passing this iron salt, it is pretty low. We go to as low as I think 3, and when you raise it up, you go to as high as 11, 12. So,
because that is the final determining pH at which our iron will be exposed to within the matrix.
well, once you do this, then you rinse it, and after that, if you put it in distilled deionized water, you get a pH of about 7.5.
And sir, finally, after synthesis of nanoparticles inside your matrix,
Yes.
sir, you determine capacity by titration, or is there any other method?
You determine capacity by?
Titration method.
No, it's just regular uptake. You just do run an isotherm.
Oh, by isotope.
Yes.
Good.
Very good. So, those are the things to keep in mind, that this 45 to 60 milligrams looks low, but I think it's pretty decent in terms of its performance. And I'll show you performance data. Everything in the end, it has to meet some benchmarks related to performance. Okay, so so that's the iron. This one, of course, has no iron because this is just copper. And this one, again, it has little lower iron capacity, because now you can see there is already copper sitting in there. It will not want iron to be associated with iron oxyhydroxide. So, anything else that I wanted to say? I don't think so. Any questions about these 3 forms?
Well, the selectivity and uniformity which you are talking.
Yes.
Uniformity of the nanoparticle.
Yes, uniformity of the nanoparticle.
Since the size varies within the same material also.
The size does vary. The question is, as we were just listening to a few moments ago, we typically say the lower the size, the more the surface area per unit weight, and the better the performance. It's not necessarily like that. That's why I'm saying this 15 to 30 nanometers gives us the best performance. Why? We have some ideas, but we don't know the full answer. Okay, very good. So once you make these resins, now you are ready to see how good they are. And so that's what I was saying, that you look at the nanoparticle size and you try to make as much uniform, and these are highly amorphous, as you can imagine. So it's not as easy. Now, we had a question as to how do we know the uptake capacity. It's through a regular isotherm, and the isotherm not only gives us the uptake capacity, it also gives us the separation factor. I'll talk more of the separation factor in the tutorial. All I can say right now is that this is what is known as the 45-degree line. The more you are to above the line, the better the selectivity. In this case, we are looking at phosphate chloride. So the more this curve is pushed this way, away from this 45-degree line, the more favorable is the phosphate chloride exchange. And if I go to the other side, then it means it's unfavorable. The standard ion exchange isotherm principles. Okay. Now we come to the question that was asked, well, why do we get this selectivity? And the answer is very straightforward, that we know, and I have this, we know that if we are looking at competition, which we are, and this is now in terms of the iron oxyhydroxide, if we are looking at competition for phosphorus over chloride or sulfate, we know that chloride sulfate, they form only outer sphere complex. This is geochemistry, coordination chemistry, it tells us very clearly. So there are all these water molecules that are present. Whereas if you look at, I just erased it, but if you look at either diprotic or monoprotic forms of orthophosphate phosphorus, then we know that the bonding with the oxyhydroxide is an inner sphere complex. So it can be monodentate, as in this case, it's only PO4 minus 1. But if it is PO4 minus 2, it is bidentate. And so you immediately see that pH plays a very important role, because if this is your governing species, then the equilibrium capacity will be low. It will be pretty much half of this, right? But this will be much more stronger, this bond, I mean. So keep in mind that there are two sides to this story. One is you are removing phosphorus. Yeah, you want to remove as much phosphorus as possible. Wonderful. You want to remove phosphorus as much selectively as possible over chloride, sulfate, nitrate, bicarbonate, whatnot. Wonderful. But you also have to recover the phosphorus. So you can't really come up with a bond that will be so strong that it will never break. So I will just show you one quick page from a publication that will give you a much better idea. Because when we are looking at these bonds, what are these bonds? These are basically van der Waals, hydrogen coordination. So let me.
In this case, two interaction. Lewis base at acid base means it is with hydroxide, means metal oxide.
Yes.
And Coulombic means with functional group.
Coulombic means the charge. So this is -1, this is +1. Minus, minus, plus, minus, plus. So this is bidentate.
So there is a two interaction. Lewis base with there is a two interaction.
Lewis acid base means that this oxygen is donating a lone pair of electrons to this. That is the standard definition of Lewis acid.
I'm saying that in this, after synthesis of nanoparticle inside your matrix, there is a functional group also, as well as iron oxide, metal iron oxide.
So right now I'm not talking about the functional group. This is just the hydrated iron, iron oxyhydroxide. It's only that surface that we are looking for. But the same thing holds for copper as well. So there's no difference really in terms of the complexation. Inner sphere or outer sphere, that does not differ. That's all I'm trying to say. Yeah. It's just electrostatic. As I said, this one is -1, it will bind to this positive one. But that binding is just based on the charge. It has nothing to do with what are the species. But when we are looking at Lewis acid base, then what is donating the electron, that is important. This is oxygen. And in this case, it is nitrogen. So nitrogen, as you know, is a much better electron donor than oxygen, stronger. So we have to keep that in mind as well. So before I get to this, let me change tracks. I'll show you something which will give you a little better idea. Give me a couple of minutes, please, as I organize myself. Okay, this is a very good slide because it tells us that how can we look at a process in terms of both performance, in our case this is phosphorus removal, but also the reversibility. So you see, if I have a redox reaction, then we know that this redox reaction is almost irreversible. If it is a precipitation dissolution reaction, more or less this is irreversible. So when we want an ion exchange process where we are recovering something, removal and recovery, then we have to basically be in this reversible. The free energy change, the delta G as we call it, standard the Gibbs free energy. That Gibbs free energy in terms of kilocalorie per mole cannot exceed, I would say, 5 kilocalorie per mole, 6 kilocalorie. Because if it is, let's say, 100 kilocalorie per mole, no way can you then recover. So, when we say, well, nitrogen is stronger than oxygen, yeah, but both of them are in this zone. Keep that in mind. Because if you go to, there is, of course, there's an overlap. Because if you go beyond this, you cannot reverse them. So keep this in mind.
Sir,
Yes.
during when you will mail, please send the document also.
Yes, I know. So now we talked about the pH and we have talked about the pH a lot, but I think it's so important that we cannot stress it enough. Because keep in mind there are two things going on. Of course, we talked about the speciation of phosphorus, and that is very standard 2, 7, and 12 triprotic acid. But now you have to overlay this in terms of the speciation also of the iron oxyhydroxide, because that also, as you see, the FeOH2 plus kind of starts to dip, maybe pH of 5, and FeO minus takes up at around pH of 11. So why is this important? This is important because this is the pH at which you are removing phosphorus. This is the pH at which you are releasing the phosphorus. Okay? But what it also means is that when you are removing the phosphorus, you are mainly, ideally, you are in the H2PO4 minus. Because if you increase the pH of your solution so that you can say, well, I want a little stronger bonding with the divalent species, you're not going to get it because the divalent species, let's say at a pH of 9, will not bind very strongly with FeOH. FeOH is uncharged, right? So all these things one has to keep in mind. And the idea here is not really to kind of make it very complicated. All I'm trying to say is, if you make a claim that you have a sustainable process, then all these things you need to be aware of. You cannot just come up with a process which says I am removing so much phosphorus and then forget about everything else. That will not. Okay, so then now we understand the theory, our thought process, how it is translated into theory. Now, how good is the performance? And of course, this is all lab scale. So, what do you do in the lab scale? You take this resin, pack it in a column, which I'm sure many of you have done in your labs as well. And you make a synthetic solution. You pump the solution through the column, and at the effluent of the column, you have a pH, online pH meter, and you have a fraction collector where you are collecting your effluent based on so much volume passed or so much time passed, whichever way you want to look at it. And yeah, that's it. Any questions about the experimental setup? So pretty straightforward. Now comes the performance. Sorry. Don't know why there's a problem here. Are they? No, no, they were column profiles. Now they have become blank. I think it's some it may have detected some. I will go to a different file. I have another file. So give me a couple of months. I'm sorry. This is based on the PowerPoint version, I think. Okay, so this is a different presentation, but you'll get the idea. It's the same kind of idea. So we we packed these materials in a column, and we ran a synthetic solution. That synthetic solution had 4 milligrams per liter as phosphorus, 4.25. Why 4.25? Because that's typically the range that you get in a wastewater treatment plant effluent. Town where I live in Dartmouth, you go to its wastewater treatment plant, which we have gone many times. When we collect the sample after disinfection, they do UV disinfection. After that, it's usually 4 to 5 milligrams per liter. Okay. And then sulfate is much higher because that's what you typically see. Chloride is very low, but chloride doesn't really. It is not a strong competitor. Sulfate is a much stronger competitor. So the way you look at is you look at in terms of bed volume. What is the bed volume? I'll explain that. So when we do a column, this column, of course, this is a lab column, but the principles remain the same. This column has a certain diameter. In this case, it is 10 millimeter. And when you load this material and water together, I mean, this material is in a water column, you can say. So it has a certain height. And this volume, the pi divided by 4 d square times h, that is one bed volume. So let me show it to you on this. Why do we do it in terms of bed volume? Because then it is normalized. It doesn't matter whether it is a 1 meter diameter column or 10 centimeter diameter column, because we have normalized it. We engineers always like to normalize things so that it is independent of the size. So one bed volume is basically the volume occupied by this material plus the water. And so as you see now, it doesn't matter what is the diameter and what is the height, because if I scale it up, then if I'm still reporting it as bed volumes, the performance will remain the same. Okay? So that's what we always do. We report it in terms of bed volume so that you immediately know that if phosphorus breaks through, what we call a breakthrough. Breakthrough is when, as you see, you put this water, which has 4.25 milligrams per liter as phosphorus, and it runs through the column. And as it passes through the column, it takes a certain amount of time, right? I mean, let's suppose we have this water molecule which has phosphorus in it. It comes in here, meets the column, and then it slowly goes down the column because it has a certain velocity. We call it SLV, superficial liquid velocity. In that velocity, it has to travel so much of a distance. So this much distance, the height of the column divided by the velocity is how much time it takes for this molecule to come from here to here, top to bottom. And that is what we call the EBCT, empty bed contact time. So in the afternoon tutorial, we will be heavily using two terms, E, C, E. And SLV, superficial liquid velocity. Not these lines. So, what are these terms? Let me just explain. So, you are bringing in water at certain flow rate, so many liters over so much time. So, SLV is nothing but Q divided by the surface area, pi divided by 4t squared. And EBCT is L divided by this. Okay. So, now why are these important? These are important because when you run a column, there are some column dynamics which one has to be cognizant of. And column dynamics, this give us some guidelines. So, in this case, when you are running a PLE, a polymeric ligand exchanger, the guidelines are that your empty bed contact time should be at least let's say 3 minutes or something like that. So we have to maintain that, right? And so now you pass this column. What's going on is that for let's say 300 bed volumes, in this case, this is the one is tau HFO, this one is HAIX, and this is tau HFOCU, this is tau HFO, this is HAIX, this is tau HFO. Okay. So this resin for 300 whatever 20 bed volumes, you were passing this phosphorus rich water, which is phosphorus coming in at 4.25 milligrams per liter. But by the time this water travels through this pipe and comes out, that phosphorus is removed. That is what this process is all about. And when this bed becomes saturated, it cannot hold any more phosphorus. All the sites are now occupied. So if you still keep running the water, the phosphorus, what we call, breaks. So the question then is, the longer the time it takes to break through, the better your resin, at least in this phase, the removal phase. So all you can say is that these two are more or less the same in terms of performance, in terms of removal of phosphorus, whereas this one, the column runs for a much, much longer time. Okay? That's all that we can say at this stage. Okay. So in this case, the TBCP was 3 minutes. All right. Questions? So it is 1:30. Okay. We have time. Sorry. So we will go, we'll move ahead. Now, when this column is exhausted, when you are passing phosphorus-rich water, initially you were getting phosphorus-free water, but when you start seeing phosphorus in your effluent, that is when the breakthrough has occurred. So then the time has come to generate the resin. You stop the flow, you pass the regenerator. And in this case, this is tau HFO. When you pass the regen, so sorry, this is the exhaustion run. This is another column where it is at a much higher rate. But I'll come back to this. Let me go ahead and talk of. So, as I was mentioning in response to a question some time ago, why does this process work? Why is the selectivity? In this case, if you look at the bonding between copper and phosphorus, there are two paths going on. One is the Coulombic interaction. Copper is positively charged, the phosphorus is negatively. So that bond, but this bonding will be the same whether this is chloride or monovalent phosphate or chloride or nitrate, and it will be the same if it is divalent phosphate or sulfate, for example, because it goes only by the charge. You know the Coulombic force, right? K1Q2 over R square. So that one is more or less the same. The reason this is so selective is because you now have this Lewis acid base interaction. So the oxygen in orthophosphate phosphorus can, or in the phosphorus rather, not the oxygen, the phosphorus can donate a lone pair of electrons, and then when one donates it to the copper, then forms a very strong Lewis acid base bond. That's what gives this the selectivity actually. But once you exhaust the column, you have to regenerate it. And when you regenerate the column, there are two things that one looks at. One is that how much of this phosphorus that was on the column can you take it out? And you would say, why should it be 100%? Well, theoretically, yes, but 100% getting out is experiments, you don't reach that. That's one. The second thing is, what is your purpose? Your purpose is to treat the water. Your purpose is to remove phosphorus from the water. Okay. So you are treating, let's say, 100 liters of water. You are passing 100 liters of water. It has phosphorus of 4 milligrams per liter. The water coming out is 0 milligrams. So 0 means non-detect. There is no such thing as 0, as you know in analytical chemistry. It's all non-detect. So it's non-detect. You have treated that with 100 liters of water. Now, when you are regenerating it, your regenerant should be as low volume as possible, because that's what makes this process attractive. So, how much of the phosphorus you are getting out and over what volume of regenerant. So, in regeneration, what we see is that we see a very marked peak. Another different color. So let us suppose we have two regeneration scenarios. Regeneration A, regeneration B, two different materials. Both of them are equally good in terms of removal of phosphorus. But when you regenerate, A, as you see, it has a very pronounced peak, and the drop, the rise and the drop both are kind of symmetrical and very compact. That is ideal. Whereas in this one, you get a pretty sharp rise, but then the drop is gradual and there is this long tail, which means not being able to get out most of the, a little of this. So what I'm trying to say is that when you regenerate, you want your regeneration profile to look as much close to this shape, A shape, as possible. And if you get B shape, then you have a little bit of a problem. So in this case, what? Yeah.
Means we need less bed volume.
We need less bed volume during regeneration. Yes.
So for regeneration, we use high concentrated of salt.
Yes.
Suppose in this case, suppose in part A, I am sending approximately 5% salt, and for B, suppose it is cheap salt compared to A. If I say
No, I'm saying this is the same kind of regenerant. Just to give you a comparison, yeah. If you have a different regenerant and if you then look at the cost of the regenerant, we are not. We're just trying to say that when you regenerate, you should get as much out as possible in as little volume as possible. That's all I'm saying. So this one, you see, it is not perfect, but it is very good because in, let's say, 18, 19 bed volumes, you have been able to get out. And in this case, I have data to show that it's about 90%, 91, 92% regeneration efficiency. So I could get out 92% of the phosphorus. I am using 2.5% chloride plus 2% sodium hydroxide. So the point that I'm trying to make is that the exhaustion curve is one part, how much phosphorus water you are able to treat, and then the regeneration also is very important. Now let me see if I can go back to my original file. Okay. So if I look at Dow copper, which is again this one. So I take the Dow resin, I preload it with copper, and now I put it in the column and then it runs. So when that's the case, when you regenerate, see that your regeneration you can do at low pH as well as the high pH. In other words, the pH doesn't really play a very important role. This is 2% sodium chloride. And you see in both cases, you get very good curve. In 20 bed volumes, you are getting out all the phosphorus. How much? 87%. In 15 bed volumes, you are getting out the phosphorus. How much? 89%. So these are very good regeneration curves because they are getting out. You can say, well, why is it only 90%? Why not 100%? That never achieved. You are getting out in a less volume, and as you see, the lower the volume, if you have the same mass, then that means higher the concentration, right, at its peak, which is great because you want that when you are precipitating. Something going on with the version. Okay. So then we come to the Dow copper into which we have these nanoparticles of nature. fix this before. Let me close this and let me try to open it again. Some recovered files that have not been opened. Like let me now try to reload this file. I think there's some problem when I try to load. Again, because they have become corrupted. Different slides have and slides. It is not possible to recover the lost information. So what I will do is over lunch, I will go back to an earlier version of this. Because I think some of these figures have been lost. Okay, so let's just look at Dow copper HFO. This is again phosphorus going in. This is the different column going in at 2 milligrams per liter. But you see it is performing better because the breakthrough is at whatever. And when we try to regenerate, what do we see? We see problem in the sense that there is a tail. As you see, if this were like this, that would be so much better. Now we have this tail which goes on, and that means that there are some issues with the regeneration. And what I think we will stop here because I have to recover this file, and uh, when we come back, when we come back. Okay, okay. Yeah, when we come back, I'll talk a little more about the column performance part, and then we will do a design. We will do a design of a column where we will look at, well, how much, what should be the size, how much water it will treat, and all that. So I apologize. This thing was kind of sudden. I don't know why this happened. I think I have an old file.